So now let us start how to calculate the backpropagation. Actually, the backpropagation algorithm is the most commonly used training algorithm for feed-forward network. It uses two different steps. First is the calculation of how much change in the weight of neurons affects the total error, and this is equivalent to the partial derivative of E total with respect to the given weight or gradient with respect to the given weight. And the second step is updating the weight of a neuron by subtracting the partial derivative of E total with respect to the given weights or gradient with respect to the given weights from the old weight of the neurons. So suppose we want to apply the backpropagation and update the weight of W21, then how we will go through. So we will first calculate the gradient or derivative of E total with respect to W21. After the calculation of this weight, we will update the weight of W21 by using this formula. So this is our formula to update the weight of W21. After updation, it is W-21, where W21 is the old weight of W21. So you can see the old weight of W21 here in the old network. So this is W21's old weight, 0.25, that we had taken earlier in the entire calculation. And after that, nu is the learning rate. We can generally use 0.5. This is used, this value generally represents how fast you want to see the network converge, and this is our derivative that we calculated here. And after applying this subtraction, we get this value. So the new weight of the updated weight of the same node W21 will be like 0.20. So this is the weight updation process by using backpropagation. Now the next important thing is how to calculate this derivative. This is the most important part of the entire calculations. Now to calculate the gradient with respect to W21 or partial derivative of E total with respect to W21, we use this information that here error propagates this way, and from this node it will propagate like this, and from here it will propagate like so this is the way to propagate the error. For this here it may be like this, and from here it may be like this, and from here it may be like this, from here it may be like this, and so on. So this is the way to propagate the error. So now we use this information for propagation. Now we can divide the entire calculations that we made for O1 is, first is the net O1 and second was the out O1. This is net association function and this is sigmoid function. So we will use this information that our error propagates in this way, and we use this information with these derivatives and apply some chaining algorithm. Then our dE total and divided by dW21 will be equal to, it will be expanded, first out 1 and then it will go through the net O1 and then so this is the basic chain rule to represent the error propagation path. Now how to calculate DE total. Now let us calculate the first part of this derivation, DE total divided by D out1. As we know that DE total is actually equivalent to the sum of two errors as we calculated here. You can see here also. This is just a simple derivation function. If you know the differentiation, very intermediate differentiation, then it is just nothing. So how to calculate EO1 means error at first output. So this is the formula for error of first output, like given output. So we just put this formula here plus EO2, we put this formula just here and calculate the derivative with respect to out1. Now if you apply simple differentiation, then you will get this intermediate output and this will be equivalent to this output. Now you know the given output and out1, this is here. Given output and out01. So the value for this derivative is 0.7411. Now let us calculate the second part, D out1 divided by net O1. Now you know that out1 is a sigmoid function and it is related to net O1 because earlier in the calculation we have used these things. For example, to calculate the O1 we use this formula, and to calculate the out1 or sigmoid function we use this calculated net O1. So you will use this two outcomes here in the calculation for the next step. So our D out1 will be replaced by this. We'll take the derivative of this. Now you can validate the result of this sigmoid function with respect to net O1 through a very simple Wikipedia article. Just open the sigmoid functions. You can see the property of sigmoid functions. If a sigmoid function is represented by st, then its differentiation will be like st into 1 minus st. We use the same funda here. So our sigmoid functions in the form of D out1, it will be equal to out1 into, and we just put these values because we already have these values calculated here, out1. So thus our second value is already calculated. Now to calculate the third derivative, this is net O1 divided by net O1 derivative W21. So now let us calculate the third one. Now for this we will use the formula that we use in the forward pass here. This is the formula that we used here for in forward pass. We just use this here in taking derivatives with respect to W21. So the derivative just apply simple differentiation, that all will be 0, and due to the presence of this, the differentiation will be result in this. Now the final output will be just a multiplication of all three results that we calculated, and which is 0.0931. We use this information to update the weight of W21. So this is the first phase of weight updation. By using the same way, we can update the weights of W22, W23, W24, W25, W66, 26 and so on. So this is a very simple step. Now let us start how we can update the weight like W11, W12, W13, W14, W15 and so on. For this we will use some error propagation information that we calculated here. So now how to update the weights of the W11. So as usual it is very simple. First we will take the derivatives of dE total, dW11, and our next step is use this information to update the weight of W11. And how we can do this? This is very simple as we did earlier. So here our weight updation scheme will be our original weight of W11, which is 0.10, and this is learning rate that we already discussed, and dE total derivative with respect to weight W11, which we are going to calculate, and based on the entire calculations we can get the updated weight like 0.1014 as a new weight for W-11. So now the main step is how to calculate the dE total derivative with respect to W11. As earlier we discussed, in the calculation of error propagation, back propagation, we generally show that error propagates like this way from here, which resulted in change in this error, and after that this, which will, and similarly from here it will propagate like this and so on. So this is the path of error propagation, and all error propagation just involve error propagations from output layer to association layers. So we need a chain rule, and this chain rule will associate the connection like net H4. Just we break the H4 into two parts, and which is net H4. This is net association outcome of H4, and out H4, which is sigmoid outcome of sigmoid functions calculated on H4. So error will propagate from here to here, and after that from here to here, like that, and from there we can link it with W21. So now let us expand this derivation with this chaining information that we have here. So it will be like E total derivatives by derivatives of output H4, again D out H4 by derivatives by D net H4, and we use D net H4 and take derivative with respect to W11. As we know, we have total three parameters, first, second and third. So first is E total by T out dE total, means derivative of E total with respect to out H4. So it can be calculated as usual. E total is equal to sum of two errors by with respect to derivatives of out H4, which is equivalent to this. Now how to calculate derivative of E01 with respect to out H4? D01 means derivative of O1 with respect to out H4 generally connects the with this derivative. This is again has two parts. First is out H1, out O1, and net O1. So it will again get the connections like this and this. So this connection is represented here in a chaining rule. So DEO1 divided by DEON's EO means first output's derivative with respect to out O1 into out O1's derivative with respect to net O1 and net O1's derivative with respect to out H4. So now let us calculate each step separately. This is again very simple, as we already know how error at first output is calculated, which is this formula here that we used earlier. So we use this formula again here and put it back and take the derivative, which is again minus 0.7411. Again next part is D out1 divided by net O1. D out1 net O1 we already calculated, we just define it again. This is D out1 is actually 1 plus e to the power minus net O1. So we'll use just replace this formula here, and after calculations we will get 0.1818. Again net O1 derivative with respect to out H4, which is calculated by taking the expression that we derived in forward passing. So this is the derivation and we take, and this is the final outcome. You can find that some calculations like D out1, D net O1 is already completed at the first layer of error propagation. So we can also put these weights here directly. So after putting all the weights, we have DEO1 is equal to this weight. Now the second part of the same function, here we calculated this part only. So now how to calculate this part? This is again very simple. DO2 by H4, we just expand it like this. Error propagated from out of O2 to net O2. So this is the expansion through chaining rule. And after the derivation, first of all we will calculate this part. We just take the expression of this from forward propagation scheme. This is our net O2. We use this. Take differentiation, and after that this will be the output. Second, this is out O2 is the sigmoid function. So and in sigmoid function we feed this part here to calculate the sigmoid functions, as we did here in the calculation of forward processing step. So we just use this formula. Here to calculate the differentiation, and with respect to the property of sigmoid functions, so this will be our outcome. Now the next part of this derivative is derivative of error at O2 divided by O2 with respect to output O2, out O2. So this is very simple. This is again, we just expand the error calculation formula. This is our formula. Taking the taking the differentiation, we get this output, and by putting the value we can easily get the result. For example, our given output, as we already know, the given output here is from the starting stage. This is our given output for second node O2, which is 0.98. Now we use this in calculation. So our given output is 0.98, and output O2, which we just calculated through forward processing, is 0.8135. We use these two values. And this is the outcome. So our final DEO2 is equal to just a product of all these three derivatives, which is equal to this. So our E total, derivative of E total with respect to out H4 is equivalent to this, and these two parts we already calculated above, and it is equivalent to this. Now the next part of the algorithm is d out H4, means derivative of out H4 with respect to net H4. So calculating the derivative of out H4 with respect to net H4. For this, actually out H4 is a sigmoid function, and for sigmoid functions we already derived this result. Derivation of derivative of sigmoid functions, we already know that it is the output. So this is the result. Similarly, calculation of net H4. Net H4 is a association function. So we again use the association expression that we derived in calculation of net H4 in forward processing step, which is our forward processing step, net H4 calculation. We use this expression directly here and calculate our values like this. Our B2 is the bias, which we already know it is. Now after differentiation we will get this value. So this is simple differentiation, and after that we can easily calculate the derivative E total with respect to weight W11, which is equal to the product of all these force that 2 hairs is calculated here, and E total that we calculated earlier here. And by using this outcome, we can easily calculate the updated weight of W-11, updated weight of W11. Similarly, we can calculate the weight of W12, update the weight of W13, and so on. Now, how to propagate the error through the first hidden layer. So this is slightly more challenging. After that, everything will be very clear. So now, how to propagate the error here? So error propagation work like, suppose we just consider this connectivity, then we can see a very simple trend of error propagation. Here it is net association function, net O1, sigmoid function, out O1. Here again it is net H1, out H1, sorry, net H4, out H4. Here again net h1 out h1. So now you can easily see the trend of error propagation. Error propagates like this. And use this connectivity information to expand our derivation chains, or use the chain rule. To update the weight of W1, we first take, as usual, we take the derivatives of, we calculate this derivation. Now by using this weight derivative of E total with respect to W1 and new in updating the weight of W1, which is a new updated weight of W dash. Now the main issue is how to calculate derivation of E total with respect to W1. As we earlier discussed the error propagations, so now in this case how to expand or how to apply the chain rule. So to expanding this derivation, we just consider on this relation. So it will be like error as error propagates from this direction, Sukhdev. So it will be equivalent to derivative of E total with respect to out h1, again derivative of out h1 with respect to net h1 as propagate like this, derivative of net h1 divided by with respect to w1, which is this. So this is the chain rule. Now we will calculate every equation one by one. So now we will calculate each part of the derivation one by one. Now let us start with this. This is net h1 and w1. So such type of relations between weight and net h1 is available in the expression that we get in the forward propagation step in the calculation of net h1, which is here. So we will use this expression here directly. And take a differentiation, it will be equal to I1, which is 0.2. Now similarly the second is just same as I discussed, out h1 by net h1. This is very similar to our previous calculations. Out h1 is a sigmoid function, so we will take the derivatives of sigmoid, which is equal to this, and finally by putting the value of out h1 and that we calculated earlier, we will get these derivations. Main part of the entire calculation is this, because it connects the entire error propagations from starting to the current phase, to the current state. So we calculate the E total, derivative of E total with respect to out h1 from path h1 to h4, because there may be several paths possible in the error calculations. For example, error propagate to h1 through this path. This is first path. Second path may be like this, after that this. Third path may be and again next path may be like this. First this error propagates and then it will relate here, then here, then here. Next may be like here from here and then here from here and then here from here and then here from here. So there may be several paths to get the error propagation. So we will get through just one path to demonstrate how we can calculate. So our path is this way to calculate the error propagation. So in this case, error propagations will be derivative of EO1 with respect to out H1, derivative of EO2 with respect to out H1. So first we will calculate this derivation. This derivation is very simple. It contains a long chain. Derivation of out error O1 connected to out O1. Out O1's error is connected to like this. Connections can be considered as like this. Net O1, out O1, again net H4, out H4, again net H1, out H1. So the connections will be like this. So this is presented here in this chaining effect. So we just going till here as our derivative with respect to out H1. So it will be like out O1, net O1, net O1, out H4, out H4, net H4, and again net H4 with respect to out H1, and so on. Now we will calculate each of the derivatives. We have to just calculate this part of the derivative, net H4 by out H1. So how net H4 and out H1 is related? So we already have relations between net H4 and out H1 from our forward passing calculations. You can see how net H4 and out H1 is related. We'll just take this calculations here. So we just put that formula, that expression here, and after that differentiate. This will give you the derivation of net H4 and out H1. Similarly, net H4, out H4 derivative with respect to net H4, this derivative, and the last one we already calculated in the previous step. So we just replace the value of these calculations here and we take another path also, as we discussed, 1 to 5 and then 5 to 1 and so on. So all other three paths results are there. This is the results obtained from path H1 to H5. Sorry, this is from path H1 through H6. And after that getting the final results, which is dEON beta derivative of EON with respect to out H1. Similarly, we can calculate the derivative of EO2 with respect to out H1. In this case, our propagation phase will be for output O2. It will be like use this type of propagation, and we use this information in calculation of final derivatives by using chain rule. So derivative of EO2, this is our EO2 with respect to out H1 from here can be calculated by using this type of chain. So EO2 will be, we will take derivative of O2 with respect to out O2, out O2 with respect to net O2, net O2 with respect to out H4, out H4 with respect to net H4, and net H4 with respect to out H1, which is here. For most of them, we can easily get the solution that we calculated earlier. So we have to just put the calculated solution here. This is our result when we take path from H1 to H5, and this is the path result when we take path from H1 to H6, and this is the final error. So our A total will be this. So this is the total error. Now E total with respect to W1 can be calculated by using this formula. These two I have already calculated. So we just put this, after applying this error calculation formula, we get the updated weight of W1. So this is the way. By using the same way, we can update the weight for W1, W2, W3, W4, W5, 6, 7, 8, 9. So this is the process. So this is the first stage to use the combination of three algorithms. First is forward pass, second is error calculation, and third is back propagation. We apply the combinations of all three, sequence of all three algorithms, and update the weight, and we will continue until we get optimum weight for all the nodes, optimum weight for all the weights W1, W2, etc. for each of the layers. And this is our final training of a deep neural network. Now, how the test phase work? The test phase is very simple. Suppose we have given some input like 0.3, 0.7, 0.9. We just pass these outputs, these inputs to these layers, and apply only forward pass, no backward processing or error calculation. So after the forward pass, we will get the output, and based on the probability associated with the output or value associated with the output, we can define the class for these three inputs. So the training algorithm, so the testing phase of the deep neural network is very fast because it just uses forward pass algorithm. But the training phase of the deep neural network is little time taking, or we can say that it is a time taking process. Or there are some issues like overfitting with deep neural network. The main reason are these neural networks are prone to overfitting because of added layer of abstraction, which allows them to model rear dependency in the training data. But a lot of methods, regularization methods like unit pruning or weight decay or sparsity can be applied during the training to combat such kind of overfitting errors. So these are some references that can be used in further study of deep neural networks.